For the much briefer introduction than I was led to expect. And thank you to the organizers for inviting me. This has been a lot of fun, both to see everybody and hear all the exciting science. And of course, I must start by celebrating Rodrigo and his birthday in 4 months. Rodrigo is my scientific older brother, and I've known him since 2008, which is always been very nice. And it's good to have nice relatives who are very successful ahead of you. So today, I'm going to tell you what I think is a very interesting story about a new way of getting Majorana Zero Modes in two-channel Kondo physics, which may actually be able to sort of braid them around and actually potentially be useful for topological quantum computation. This is a highly theoretical story, so it's very far in the future, but I think it's very interesting. And this was done with Victor when he was my postdoc, and with Milan Kornjacha, who was my student at the time. So we'll start with sort of an outline to give you a sense of where we're going. So first, I'm going to review a little bit how you get Majoranas in two-channel Kondo impurities. So this is an old story and has been known for quite a while, since when Eduardo was at Rutgers, working on Majoranas in a different Kondo problem. And there's, this is very interesting, but the downside is it's not really relevant experimentally. You can realize two-channel Kondo impurities, but they're always in metallic systems, and so the Majoranas talk to one another and are no longer Majoranas. And so, they're physical defects. There's no way to really braid them around. And so our goal is to find a kind of more amenable two-channel Kondo impurity. And so we're motivated by the story of Kondo holes in the single-channel Kondo lattice. And so I have to tell you the story of how you get something similar in the two-channel Kondo lattice. And so this will be the story of Hastatic order, which I've been working on since 2013, so for the past 10 years. And I will try to keep it very simple. It's somewhat a complicated story, but I think a very cool result. So, and then we'll go to the defects, and at the end we'll talk about some highly theoretical potential experimental realizations. All right, so first, what is a Majorana fermion, right? They're real neutral fermions. They have these kind of properties, and you can combine two Majoranas to form a single complex fermion, which we're calling F here. So these gammas are our real fermions. There's 2 of them. And so this is, an old story. This is potentially useful for non-universal topological quantum computation, where you basically, the fermion number encodes a 2-level system. And so potentially you can use these to sort of braid them and realize different quantum circuits. And the goal here is not just Majorana fermions, as you might find in high energy theories of neutrinos, but to find actually localized Majorana Zero Modes. So where your Majorana fermion commutes with the Hamiltonian, or at least it commutes up to some sort of localization length scale. And this idea then is that these are actually not just Majorana fermions, but they're non-abelian anyons, or a type of Ising anyons, where if you take 2 Majorana fermions at defects that are maybe a little further away than in this picture, and you exchange them adiabatically, you're going to braid them in this fashion, where you pick up this plus or minus sign. Okay, so, and there's been many possible realizations discussed in topological superconductors, in spin liquids and nanowires, but I think it's safe to say there's no sort of nice realization. This is also not yet a nice realization, but I think it's always good to have options. And anyway, so now I tell you about the two-channel Kondo physics. So this is the two-channel Kondo model. We have 2 kinds of conduction electrons. So they have both a spin index sigma and a channel index I'll call alpha. And all sort of 4 fermion species are going to screen a single local moment. So I like to give this example because this is really something that does occur in nature. And so if you have something like praseodymium 3+ or uranium 4+, you can get a ground state that has 2 F electrons. And if this is in cubic symmetry, then your, you have strong spin-orbit coupling, you get J equals 4, it gets split by the crystal fields, and you can end up with this situation where you have a ground state doublet that is completely quadrupolar. So it has no dipolar degrees of freedom in the doublet, and so you can sort of draw the electronic charge density, and you see, this is coming from F electrons, so it's a little bumpy, but it's essentially, one is squashed and one is elongated. And so this forms a quadrupolar doublet. So it's a pseudo-spin 1/2 doublet, but it can undergo all of the same Kondo physics. The conduction electrons can also sort of form these 2 kinds of different shapes, so they also have quadrupolar degrees of freedom. And so they can screen this local moment, but they still have their spin degrees of freedom. And so these, in this situation, provide the channel, which is protected by time reversal symmetry. And so in this particular case, these 2 channels, which I've here labeled by alpha, and all of these are Einstein summation. So these 2 channels are degenerate in this case. In other cases, you can sort of tune the ratio of these couplings. But what's really interesting is when they're exactly equal. So the local moment ends up being overscreened. Essentially, one type of electron tries to form both types of electron try to form a Kondo singlet at the same time. So you leave an extra spin, and then that tries to get screened, and it goes on. And so you end up with a quantum critical point. And this is sort of a sketch. You get a Fermi liquid in channel 1. If your J's are not equal, either channel. But in between is the really interesting place. So the vertical axis here, which is not shown, is temperature. OK. And so what's really interesting here is you have a single Majorana that is left at your impurity in the ground state. So you have a ground state entropy of 1/2 R log 2. So here is a numerical calculation of what the entropy looks like. So you have log 2 at high temperatures and this 1/2 log 2 at low temperatures. And so Emery and Kivelson, along with many other people, were able to show that you could write this really in terms of a Majorana. So this is a simple 1D picture of this 2-channel Kondo impurity after you go through bosonization and refermionization, stuff that I don't really understand. But what you end up with is a term with conduction electrons. These are these psi's. And they're at every site in the lattice. This is a continuum model. And then you end up with a hybridization term here, where you have the conduction electrons and the F electrons. But you see they're formed into these combinations that look like linear combinations, that are linear combinations of the complex fermions that end up being Majorana fermions. Yes? So there are 2. So there's one sort of local Majorana fermion here, which is this F. That is on the impurity site. This is a conduction electron. So these ones are hybridizing, actually. And then the other Majorana fermions? OK, so there's 2 other Majorana fermions, right? So there's always an even number of Majorana fermions in your system. So these 2 are hybridizing, so they end up totally delocalized. Then the one we're sort of interested in that gives us this 1/2 R log 2 entropy is the Majorana that's on our local site. So these are these Fs. And so this second Majorana remains totally unhybridized. And then so this is sort of the Majorana that gives us this 1/2 R log 2 entropy. And then as you say, there is another conduction electron Majorana, which is the sort of antisymmetric type linear combination of these guys. And that is fully delocalized. It's part of the conduction electron band. Please. These are spin-half objects, yeah. So there's different ways that you can do this, right? So there are ways to represent the spins in terms of Majorana fermions. So you can represent a spin 1/2 in terms of 4 Majorana fermions. And then again, you have this sort of leftover unhybridized Majorana. You can also go through with the spins and do this bosonization and refermionization and end up with this theory written in terms totally of these complex fermions that come from this process. Oh, of course, yes. Yes, and that's what we have been doing. yeah. Oh.
No,
right.
yeah, done.
Yeah, no, you can also write these losses in terms of SUN spins. This is what we do when we want to look at sort of the lattice physics, which is where we're going to go. OK. All right, any other questions? Yes? Oh. Run, run.
So when you write the second combination, the F plus F dagger over 2, so this is because you're using the complex fermion, right? But in reality, I think you could just have written like one Majorana there, right? It's not that there is another Majorana. It's like an auxiliary, right? But at the impurity, there would be only one Majorana.
There's only one Majorana left, but there's two, right? So this one is the one that comes up in the Hamiltonian, but this hybridizes. So it becomes part of the conduction electron band, and it's totally delocalized. So the Majorana that's left over is this linear combination. So you do need both. Yeah, the one that people don't usually write is the second conduction electron Majorana, but that's also delocalized. All right, any other questions? It's good to have questions early while the story is still relatively simple. OK, so now we come to the problems with this, right? This is very exciting. And I should indicate there are many generalizations. If you go to other multi-channel Kondo problems, you can get different types of more complicated zero modes, like parafermions. But this is very exciting. However, experimentally, the examples that we know are all in metallic systems, because that's where you get Kondo physics, and you get a sufficiently strong Kondo interaction to induce the Kondo effect and cause this kind of quantum critical point. So these are not localized. And so they're no longer essentially Majoranas, because the Majoranas will talk to one another from two different impurities. And you no longer have any zero-point entropy, as was shown in this paper with Anna Toth and Piers and Gabby. Now, it's possible you can gap out this metallic system. So there's this proposal to apply superconductivity. Then you require a threshold Kondo effect in order to get this Majorana physics. But you still have the problem that if you're making this experimentally, you're making a defect in your crystal. Even if you have sort of a nice, you make a layer of add atoms where you can move things around much more easily than in an actual crystal, you still cannot move these things adiabatically, right? Any movement is going to really change your underlying lattice, and all of your topological protection that you might want to use for quantum computation is gone. OK, so this is sort of the interesting thing and the problem. So now we're going to come to the solution. So this is sort of our goal. We want to have mobile two-channel Kondo impurities in an insulator with sufficiently strong Kondo interaction to still give us this Majorana zero mode. So this is what I'm going to try to argue that we have found, theoretically. So, OK, so before so in order to introduce this sort of idea, I want to talk about an older idea of Kondo holes. So this is where you so this is a sketch of a single channel Kondo lattice. And in the Kondo hole, I take away a single spin. And it's well known for many years now that this acts actually like a Kondo impurity, which then gets screened, and you form sort of this local Kondo resonance. So here is a theoretical picture from this paper in 1991 where you have, a Kondo gap at the so this is the hybridization gap, and then you have a whole Kondo resonance coming from your Kondo hole. And this has been seen experimentally, but with STM, looking at thorium impurities in uranium, ruthenium 2, silicon 2. And so this is sort of an old story. And so we're hoping that, OK, we go to our two-channel Kondo lattice. And now maybe we can have some kind of defects that are going to still have this Majorana physics. And so this is sort of our goal. And the answer is yes. Defects will generally look like two-channel Kondo impurities. And because of the nature of the order in the two-channel Kondo lattice that I'm going to talk about, there's a symmetry-breaking order. And so you can get topological defects. These are skyrmions, which are very big, smooth defects. And these will still have a Majorana zero mode in them. And so these are where we're going with the mobile things. So I'm going to explore this in a very simple mean field theory, but we're talking about topological defects, and these results should be very generic. Okay, so we're back to the two-channel Kondo model. Now we're putting our spins on the lattice. So far we've only been talking about an impurity model. And I'm labeling my ground state doublet with a spin and label sigma, and my excited state doublet is also a pseudo-spin 1/2. So this is sort of where you get the Kondo physics from virtual valence fluctuations. So this is labeled by alpha, which labels the channels. And so the physics of the two-channel Kondo lattice is still a little bit up in the air, but I think we have a pretty good idea of some of the possibilities. You can solve it exactly in the large N limit, either using SUN or SPN spins. And you can also treat it numerically with DMRG in 1 dimension or with DMFT in infinite dimensions. And so I'm going to talk about just one possible phase here, which is a type of channel symmetry breaking order. So with Piers and Premi, we call this static order. And there's another group in Japan with this Hoshino, Otsuki, and Kuromoto. This called this a diagonal composite order. But really, all this is, it's not that complicated. It's a heavy Fermi liquid that chooses a particular channel to break the symmetry. And so it's just a channel symmetry breaking heavy Fermi liquid, or you can get a Kondo insulator that is also breaking this channel symmetry. Yes? Yeah. Yes.
Without breaking any symmetries? If you just look at the SUN theory without breaking any symmetries, do you still retain the Majorana fermions or analogs of that on the lattice, or do they get gapped out by the lattice scale?
Yeah, so, okay, so when you're doing SUN, everything, you represent your spins in terms of these Abrikosov pseudofermions, and there's no Majoranas anywhere. It just becomes a quadratic theory. So in the large N limit, there's no Majoranas. Yeah, and I'm not going to find any actual Majoranas in this picture because I'm going to work from this large N limit, but I will argue that you get, again, a two-channel Kondo impurity system. Okay, there's some indications that you can ask me about later that this static order is actually a non-Fermi liquid, but is still breaking this channel symmetry. So just to give you a bit of a flavor, so here is a picture of where you get sort of a single channel Kondo effect. So you have virtual valence fluctuations from a doublet ground state to an excited singlet state. So this is 1f electron to 0f electrons. You theoretically use an auxiliary boson to represent your excited state, and this effectively represents the symmetries of the Kondo singlet. And so in this picture, there is just a single quantum state here. And so there's no labels. The excited singlet has no quantum numbers. And your hybridization breaks no symmetries. I mean, it does in the large N limit, but you know that when you put in fluctuations, you end up having a crossover. So this is sort of the theoretical model of the usual heavy Fermi liquid. And when we go to two channels, so we had this, I showed you had this 2f electron ground state that could give you this doublet that's protected by the crystal symmetry rather than time reversal. And when it has virtual valence fluctuations, these are to an excited doublet that is protected by time reversal. And so to represent this, theoretically, you just say, well, now I have two bosons. They're actually packaged together into a spinner. And this excited Kramers doublet carries a channel quantum number, essentially. And so that means your Kondo singlet, which is represented by the condensation of these bosons, is also carrying a channel quantum number. So this forms a spinner, but it breaks a real symmetry, and so this must develop as a phase transition if you really have the full condensation of this. All right, and then let's talk a little bit about why this might at all be experimentally relevant.
Rebecca, sorry.
Yes, please.
What is the, if I just try to classify this in terms of reduced presentations of the point group,
yeah.
I assume you need a double group here.
Yes, this is the double group, yes.
Right. So is it easy? What rep would that be?
So it depends what symmetry in. If you're in, okay, so and I only know the F electron ones.
That's fine. We can do uranium returning to silicon too.
Well, okay, so let's do cubic. This is gamma 3. This is going to be gamma 7.
Okay.
And then the conduction electrons are gamma 8.
Okay, and then you're saying that you have something that transforms as gamma 3 times gamma 7.
Right, which is gamma. Well, no. So the order parameter is this excited gamma 7.
Ah, okay.
Which is the double. It's a doublet,
Okay.
right?
Okay. And
Yeah.
then which symmetry is broken then? Is the condensation of gamma 7?
So it's the condensation of gamma 7. So the question of which symmetries are broken is actually like a very interesting question, right? Because, and like I really shouldn't get into it now, but you notice I put here that this is not gauge invariant. So I'm skipping many details, but the actual order parameter has to be gauge invariant. So there's like 3 different bilinears you can establish that will break real symmetries.
Okay, thanks.
Yeah. And so please feel free to ask me about that later. Okay, so let's just say very briefly about some real materials, just to remind the experimentalists in the room that there is some actual connection to reality here. So you have this 2f electrons. This was originally proposed as a theory with Piers and Pramy for uranium, ruthenium 2 silicon 2, which is a tetragonal system. And we have a lot more work on that. I'm happy to talk about it. There's also these praseodymium 1,220 materials that are cubic, and those also clearly have 2-channel Kondo physics happening. And so there's possibly, if you take this praseodymium iridium 2 zinc 20 and you apply it a magnetic field to kill an antiferro quadrupolar order, there is a heavy non-Fermi liquidish region that occurs below a phase transition that could be a static order. Okay. And there's other proposals that I'm not talking about. So let's go to sort of what this looks like. So in the large N limit, I'm basically saying, look, you can form a Kondo singlet, but you have to choose sort of which channel you're forming that Kondo singlet in. So this is my cartoon where I have my local moments. And so this one is forming a channel singlet with the conduction electron spins that have the conduction electron sort of pseudo spins that have a real spin up. So the spin up here is labeling the channel. And so this is broken asymmetry. I mean, now it's just a single site, but it's broken the symmetry to point in the channel up. So in the real lattice, you have to actually order these on the lattice. And that's where life gets interesting. There's multiple ways of doing so. So the sort of simplest is to just order this ferromagnetically. And so you have essentially you're screening your local moments with just one channel. And so those conduction electrons will become heavy. The other ones are just decoupled. But you can also form sort of staggered orders where you're alternating screening with the up spins or the down spins, up, down, and so on. And you do have to be a little careful because here in the large N theory, my order parameter is really an SU2 spinner. So on each side, it's represented by something that looks like this. And you know, time reversal acts differently on spinners and vectors. Usually, the order parameters we're familiar with are all vectors, so time reversal just inverts it. You apply double time reversal, you get it back. And so this is what one uses to sort of construct antiferromagnets that have 2 sites per unit cell that still have a time reversal-like anti-unitary symmetry. To do that, in this picture, because this is a spinner, you actually need 4 sublattices to sort of construct here on like, well, let me, so you get basically on site A, sublattice A, it hybridizes with some direction, then you put its time reverse here. Here's a double time reversal where it picks up a minus sign. Here's triple time reversal where it picks up a minus sign of this one, and then you keep going. So this breaks actually an additional symmetry. It breaks inversion symmetry, and there's different ways you can do this. And you can actually physically distinguish these different capabilities. So that's, okay. At any rate, this is sort of the basic, but like this can be very complicated, but the basic idea is, look, you have these Kondo singlets, they break a symmetry, and they can break translation symmetry as well as the channel symmetry and make different combinations. Basically anything you can get in magnetism, you can get in these kinds of pictures. Okay, so in the large N, so this is just sort of to recap what we find. It's a channel symmetry breaking heavy Fermi liquid. So we see heavy Fermi liquid signatures, and we see broken symmetry signatures. Okay, so now let's talk about is this a real phase, right? I talked about the large n limit, real life n is 2. So there's, in the large n limit, we find it everywhere if you're doing SUN. And you can also look in 1 dimension and in infinite dimensions. So here's the result from DMFT in infinite dimensions. And so this is varying the temperature and the conduction electron density. So remember, the number of conduction electrons goes between 0 and 4. So this goes up to half filling, where you have antiferromagnetism. At low fillings, you have ferromagnetism. And then here, around quarter filling, you have this big region of this staggered channel symmetry breaking, or what we call antiferrohastatic order. Okay, and there's also composite pair superconductivity. There's many different options. And then you can also do 1 dimension, which was done back in 2005 using DMRG, where they found a 2-channel Kondo insulator along this line. And then my student Milan and I recently, well, Milan really did all the work, recently revisited this using DMRG and actually looking for this kind of hastatic order. We found basically a density wave version almost everywhere at strong coupling. So all of these sort of red-orange regions are hastatic order. And this region here at quarter filling is a 2-channel Kondo insulator with this staggered hastatic order. Okay, so this is to suggest this is a real phase. It occurs beyond large N theory. And now we're going to look, now that you might believe that it might exist, now we want to look at defects in this. So we're going to do a really simple model. And so I want to look at the Kondo insulator. So I want to look at quarter filling. And I want to make my life easiest, I'm just going to open up a Kondo gap at a single point. So I'm going to look at a lattice that has 4 sites per unit cell. All of this is totally general, but this is just the simplest lattice where you can see this physics. So here is what your conduction electron bands look like. And at quarter filling, you have a quadratic band touching at the gamma point. Yeah. For the conduction electrons? I don't see why it would not. I have not looked at that. I don't know that anyone has. But as long as your conduction electrons are sort of Fermi liquid, I think you still have to have this physics, yeah. OK, so I have these conduction bands that look like this. Now I'm going to let them hybridize with spins, also sitting at the same sites. And I'm going to put on this staggered order that preserves time reversal, so it's a little different at every site. But if you look at the moments, which are these excited state moments, this is sort of the pattern that they look at like. And then this is my hybridized band structure. And so let's zoom in around quarter filling. And you see that I've opened up a Kondo insulating gap. So it's a hybridization gap that's centered at the Fermi level. And so here's the density of states. And we're going to show that you get an impurity state you can get an impurity state inside this band. So for the regular lattice with no defects, of course you do not. OK, so let's look at the simplest thing. So actually, let me go back here. So here I have spins everywhere. And here I'm going to remove a spin on one of my sites. So this is the Kondo hole. And then I'm going to solve the real space mean field theory. The stars, we did a sort of very generic job, not looking at great detail, but you solve a real space mean field theory, and what you get is a doublet impurity state in the gap. So what happens when you do a mean field theory? I'm skipping all of the details. Please feel free to ask me later, but it makes it way too complicated. In the large N limit, you just get a quadratic theory, right? So usually you just have bulk heavy electrons. So here those are represented with beta. And you have a momentum, which with the broken translation symmetry, it's a pseudo-momentum, and a sort of new channel symmetry and a spin symmetry. So without the defect, you just get bulk heavy electrons. With the defect, you also get sort of a impurity heavy state here. And you can look at this state specifically, so I'll show you how we found it. And it is very well localized. So notice the defect state is here. The impurity weight is in red, so it's mostly opposite from here. This is basically like 96% F in character, and it's exactly half filled. So you find this if you just take this real space lattice, diagonalize it, and look at all of your energies. You find that you have a single state in the gap, And you can sort of quantify the amount of localization. So we looked at a modified inverse participation ratio, which looks at sort of the local F weight. And you can see there's just one localized state. These are all of the sort of heavy band states. OK, so it is, and I'm telling you it's a doublet, and it's exactly at quarter filling. So it has to be half filled. So we have essentially a pseudo-spin 1/2 defect state. And sorry, it has to be half filled, and it's also pure F. So it's coming from something that is not like originally really a local, it's originally a local moment. So in the sort of mean field theory, it just sits there and is a ground state degeneracy. But now we can put on fluctuations. So go and add 1/n corrections. So these are Gaussian fluctuations, and this will then cause this impurity state to interact with these bulk heavy fermion states. And it does so with a Kondo interaction. So this is the Feynman diagram. There's a lot of indices for the different channels and spins and pseudo momenta. But effectively, you get this kind of Kondo interaction. And so we did this calculation in real space, looking at the corrections. This is sort of the details to show you for those of people who are somewhat familiar with this. You work in a radial gauge. You have fluctuations of the amplitude and the angles of the static spinner and the constraint that's enforcing the half filling. So we do this in RPA. And after a lot of computational effort, you end up with a Kondo interaction, which is essentially a big matrix here. So now that you have this big matrix, you can look at it to sort of see what it is giving you. So it's easiest to look sort of at the diagonal Kondo couplings. So if they're diagonal in pseudomomentum, they're also diagonal in the channel. So here you get a distribution that kind of looks like this. And you see that in channel 1 and channel 2, they have basically kind of different distributions with different means. But really what you should do is just take this big matrix and diagonalize it. And then that gives you a bunch of different Kondo couplings in different channels. So if you had single channel Kondo, this would give you sort of like an S wave and a P wave and a D wave, and usually you throw away all of the other ones. Here you get 2 different Kondo channels that are essentially in the sort of original channels, and then a bunch of things that you can throw away. But these are pretty different. So they're about 25% anisotropy. So there's definitely no Majorana fermion here. So basically, you're breaking, let's see. So I think I have a picture. OK. I'll talk, let me first explain where we do find this, and then I'll explain why it's different in the Kondo hole. OK. So now we want to look at a different type of defect, which is only possible in this static ordered state. So we've broken a symmetry. We have an order parameter, and one of our order parameters is essentially like a little tiny magnetic moment that is representing the direction of the hybridization spinner. And so this has stable, although not energetically favored, topological defects. So in 2 dimensions, you get a 2-dimensional skyrmion. And so here I've sketched a picture. So we have 4 sublattices, remember, that are staggered. I'm just showing you the spins on the A sites. So it's a little more complicated than this. But this is a topological defect that you could expect that you could actually induce this and it would be stable. So this is much smoother than the Kondo hole. So we have a little bit of hope that maybe our channel symmetry is preserved better. And so again, we can take this, put this into our real space mean field theory, and just diagonalize the problem again. And so again, you get a defect state, which we identified the same way, looking at the energy. It's exactly at 0 energy and half filled. And the inverse participation ratio, it's the only localized state in our problem with closed boundary conditions. And it's very, very strong F weight. But here it's much smoother. So the Kondo hole was mainly here. This is spread out. OK. And so now we go through the whole same process, get our Kondo couplings. And you see they're much more symmetric, even just looking at the diagonal Kondo couplings. And then when we diagonalize this matrix, we find less than 1% anisotropy. So here, we really have actually now 2 channels, a local moment that's interacting with 2 channels with the conduction, the heavy conduction electrons. So we really have a two-channel Kondo impurity, and Rafael is already standing up, so I will, I think I've gotten to sort of my main point, but okay. So there is a caveat. You might worry, does it have a threshold Kondo interaction that's going to allow you to actually enter into this region? You might worry because you're in a gapped system. It turns out this Kondo coupling is actually extremely large in everything we looked at. That's basically because there's a gap, but there's also this, it's a hybridization gap. So you have all of the F states are also piled up all outside of the gap. So you get basically a strong enough Kondo impurity temperature to be in this region. And so this is our sort of main summary. And I'll just talk through this, and then we can, if you want to know about experiments, you can ask me later. So this is the Kondo coupling anisotropy. So for the skyrmion, it's very close to 0. For the Kondo hole, it's pretty far away. This dashed line is sort of the temperature, the crossover temperature above which you expect to see Majorana physics, and below which you expect it to just be totally screened out and form a heavy Fermi liquid. This is for the impurity. And so the idea is you cool your system down, you enter into this static order, you basically immediately, then you form the defect, and then as it's formed, you're screening it, and it's in this Majorana regime. So I think that's really cool. You get to move it around. And I'll stop my story here so that you guys can ask questions. But we have thought a little bit about experimental realizations. So yeah, I can go very quickly to my summary.
All right, let's all thank Rebecca. Okay, questions?
Very interesting talk, Rebecca. I'd like to ask 2 questions about the skyrmions. The first is you have this static order, and then you create this topological defect that has some chirality built into it.
Yes.
So can you figure out some kind of spin-spin interaction in this language that has like geologistic Maria type of thing that you could create this chirality, or? Okay.
Yeah. So I have to say, this is not going to form by itself.
Okay.
So there's not, okay, so essentially you can think of the static moments as magnetic moments, and you can have an effective Hamiltonian that's giving them an antiferromagnetic or antiferromagnetic ordering, and potentially you could have other terms that are maybe eventually favoring skyrmions. I don't know how to do that. It's a very hard problem. But you can also just induce these. So this is the experimental thing. These have a little magnetic moment, so they will couple linearly to magnetic skyrmions. So you can essentially put a layer. Oops. Oh, no. OK. You can put a layer. No, can I? A little bit down. All right. I'll let you. Anyway, you can put a layer of skyrmion material on top of it and essentially freeze in the skyrmion. So you're not gonna, it's not going to occur naturally, but you can induce it.
Okay. So the second question is, I keep trying to do this mapping with the vortices in P-wave superconductors where the Majoranas sit inside. And there, if you have one vortex and you have one Majorana in, there will be another Majorana around the edge of the state. Yep. Now, if you have 2 of them, then there will be one in each vortex. Yep. So would something similar happen here? Like you have this propagating Majorana if you have just one skyrmion?
No, actually, I don't believe so. So it's not, I haven't looked at it in great detail, but the other Majorana is in the conduction electrons, and it's delocalized. So yeah, I don't know too much about like if it might have a chirality. But this is sort of a localized defect, so I don't think so. The other Majorana is just totally delocalized and not interacting with these.
Okay, hi Rebecca. Very nice idea. Let me see if I understand what you did. So the first defect, you created a Kondo hole and you analyzed it. Then the second part, you did not put a Kondo hole, just look at the at a topological defect of the order parameter and the like. Okay. So the first question is, in the first case, is it a real space calculation in large N in the sense that you allow for spatial variations of the order parameter with full?
No.
No.
No, we were lazy. So you can do this, and Dirk Moore and his student did this really nicely for the single-channel Kondo hole, where you allow your hybridization to sort of relax and pick up the spatial changes. So our Kondo hole calculation is probably kind of inaccurate because of that. I think the fact that there's a defect absolutely survives.
Sure.
There may be some adjustment, and it's not as bad and anisotropic. The skyrmion is very smooth, so I think our approximation is very good here.
Yeah, but my question would be exactly that perhaps the Kondo hole might bind a skyrmion if you allow the order parameter to vary it, spatially vary. If you relax the large N in the Kondo hole case, I wonder if it might bind a skyrmion to it.
I did not think about that. I'd kind of be surprised because the Kondo hole is, I mean, it's not super symmetric because it breaks the lattice symmetry, but it doesn't have this kind of winding associated with this.
There's a very old calculation, back when you weren't even born. they took the usual Kondo lattice and within large N and solved it spatially in one dimension.
Okay.
And it binds a soliton.
A soliton, oh.
Yeah, so that's why I think might happen here. I don't know.
That's
it
very
has to be
interesting.
Done. Yeah.
I wonder if that's problematic, though. You have two impurities, and I don't know.
Okay, thank you.
It's an interesting question.
Go for the last question.
Hi, Rebecca, thanks a lot. I learned a lot from your talk, but I have a very simple-minded question. I don't know this stuff very well. So when you described the order parameter of the hastatic theory, you said it's a spinor,
Yes.
but it's a fermion bilinear, right?
Yes.
In each component of the spinor, I mean, it's a bosonic degree of freedom.
I mean,
So
in large N, it's the bosonic degree of freedom condensing, yeah.
And from your pictures, it also looked like there was some magnetism. So is it kind of like a ferromagnet or something, or anti-ferromagnet maybe?
Let me see if I can go back to this. Okay. So somewhere I have one of the order parameters written here. So if V is your spinor, you can form essentially a moment. It's called the composite moment. And this behaves exactly like a ferromagnet or antiferromagnet. There is also another order parameter that can detect sort of the sign change between sites. And so this can give you this inversion symmetry breaking that you get in the 4 sublattice case. This is, I don't have this written here, but I can show you later. And we did actually find it in DMRG. So there is actually evidence of this spinorial nature beyond this sort of simple magnetic order parameter.
Okay, so let's thank Rebecca one more time.
Okay.